Welcome to this masterclass. Let's get right to it. Today, we are moving entirely past basic, rudimentary cleaning concepts to achieve elite-level mastery over material restoration and corrosion management. If you are here, you're looking for high-density, actionable intelligence on exactly how to chemically control and reverse material degradation.
Okay, let's dive into our curriculum. By the end of this session, you'll be equipped to manage complex chemical interventions across a massive spectrum of applications. You're going to learn how to execute everything, from industrial steel descaling workflows to the absolute surgical precision required for rescuing delicate fabrics, all without risking material degradation. This is all about precision, authority, and professional stewardship of the materials we work with. Here is our roadmap for the session. We'll cover 1. The chemistry of corrosion, 2. Mechanisms of rust eradication, 3. Industrial-scale rust removal, 4. Precision treatments for delicates, and finally, 5. Troubleshooting and professional prevention.
Let's start with Section 1, the chemistry of corrosion. We have to build our scientific foundation first.
So here is the absolutely crucial point. While all rust is corrosion, definitely not all corrosion is rust. Corrosion is just a broad umbrella term. I mean, you can have aluminum corrosion or copper corrosion, but rust is a highly specific electrochemical reaction that strictly requires three things: iron, oxygen, and moisture to yield hydrated iron 3 oxide. If you remove literally any one of those environmental factors, the rust formation slows down dramatically.
Now, understanding the physical nature of the stain is what dictates your strategy. A surface stain, say a shaving cream ring on a porcelain sink, just sits on the top layer. That requires a vastly different, usually much milder, treatment than an embedded stain. Embedded rust actually penetrates the microscopic pores of concrete, stone, or fabric, which physically locks those iron particles right into the substrate. To treat embedded iron oxide, you have to use targeted chemical extraction to pull it out from within.
Moving on to Section 2, Mechanisms of Rust Eradication. There are 3 distinct chemical routes you can utilize for eradication, and you have to select your agent based on the specific route required. Removers utilize either dissolution, where mineral acids shift the iron oxide bonds and basically float the rust away, or chelation, where agents like citric acid selectively bind to the iron atoms. Converters, on the other hand, take a different approach. They actively transform the rust into a protective barrier layer. For example, tannic acid yields an inert dark compound called ferric tannate, while phosphoric acid creates a tough iron phosphate film, which is often sealed right under a polymer layer. Let's scale this up. Section 3, Industrial Scale Rust Removal. At the industrial level, we're dealing with immense scale. Steel forms intense oxide and scale layers during thermal treatment. Removing these inorganic impurities and non-metallic residues requires highly calibrated mineral acids, like hydrochloric or sulfuric acid, in a demanding process known as pickling. And listen, pickling is absolutely essential for any subsequent surface finishing or cold forming you want to do. But here's the catch. Raw acid doesn't just attack the rust. It relentlessly attacks the base metal too. Notice the difference here between an uninhibited acid attack and a professionally controlled environment. Professional 80-side inhibitors are integrated straight into the pickling solutions. They're ingeniously formulated to drastically reduce the dissolution rate of the base metal, but without stopping the necessary chemical destruction of the scale and oxide layers. This optimizes your acid consumption and, most importantly, protects the material's integrity. Precision is absolutely critical here because the risks of poor execution are massive. Underpickling leaves scale behind, which ruins future finishes. Overpickling leads to base material attack, wasted acid, and a highly dangerous structural flaw called hydrogen embrittlement. Plus, after pickling, the steel has to be meticulously rinsed to remove residual acid. This is exactly why LEAT facilities utilize hot cable cord neutralizing rinses, strictly maintained at a pH of 10 to 11. That specific pH range neutralizes acid residues perfectly, stops local anodes from forming rust pustules, and ensures a bright, passivated surface completely free of flash rust.
Let's shift gears. Section 4, Precision Treatments for Delicates.
Let's look at stainless steel. A critical professional insight here is that rust on stainless steel is almost always just surface contamination from external iron particles, like steel wool residue or hard water. It's not a failure of the base metal itself. So never ever use bleach or harsh hydrochloric acid. Those will completely destroy the metal's natural self-healing chromium oxide layer. Instead, a targeted 5% citric acid solution is your professional protocol. It safely chelates the iron in under 4 minutes, leaves the passive chromium layer fully intact, and it guarantees zero detectable heavy metals in the runoff. That makes it totally eco-friendly.
Now, when it comes to textiles, your chemistry has to be exceptionally gentle but highly effective. You start by saturating the stain with mild organic acids. Lemon juice or white vinegar work perfectly to break down the iron oxide. Then you add table salt. The salt acts as both a mild abrasive and an absorbent to physically pull the dissolved rust right out of the fibers. You blot it, never rub, because rubbing just pushes the stain deeper. And here is the critical failure point for fabrics: temperature. You must rinse exclusively with cold water and air dry. Why? Because the heat from hot water or a machine dryer will permanently bake any residual iron oxide directly into the fiber weave.
Concrete and stone present a completely different challenge because of their massive porosity. For deeply embedded stains in concrete, those mild acids simply won't cut it. You have to utilize powerful chemical cleaners containing oxalic acid or diluted trisodium phosphate, known as TSP. Oxalic acid acts as an aggressive complexing agent, literally stripping away the toughest embedded stains. But you have to allow sufficient dwell time for it to actually penetrate those pores, and then forcefully extract the solution with a pressure washer. And for sure, always wear proper safety gear here, and be ready to do post-cleaning touch-ups, because these strong acids can easily strip away decorative concrete coatings too.
Finally, Section 5, troubleshooting and professional prevention.
Before applying any chemistry at all, professional field operations dictate a very strict diagnostic phase. First, you inspect. You have to identify the true source, the surface type, and the depth of the stain. Second, you perform a controlled spot test in an inconspicuous area. Wait about 5 to 10 minutes to evaluate for any color changes, surface damage, or etching. Only after validating chemical compatibility with your substrate do you actually proceed to apply the removal chemistry. This is how you prevent catastrophic material damage.
If you're out there facing chronic, recurring stains that just refuse to budge, consult this troubleshooting checklist. Often, it's simply an incorrect diagnosis. What you think is rust might actually be hard water deposits, manganese, or tannin stains, and those require completely different chemistry. Another common failure is incomplete penetration. Your acid just didn't reach the bottom of the pore. But honestly, most of the time the failure is due to an active, untreated rust source, like a corroding pipe or a metal chair leg that is just continuously recontaminating the environment the second moisture is introduced. Take a second to really think about this quote. True mastery of the subject elevates you from simply cleaning up a mess to practicing intentional material stewardship. Preserving tools, optimizing complex industrial machinery, protecting household surfaces. It's all about respecting the craftsmanship and extending the lifespan of the materials we rely on every single day. As we wrap up this masterclass, and as you go out to implement these chemical frameworks in your own operations, I want to leave you with one critical question. Are your current workflows actually resolving the underlying electrochemical reactions, or have you just been washing away the symptoms? True professional mastery means controlling the environment, neutralizing the source, and preserving the base material. Thank you for attending this masterclass. I look forward to seeing how you apply this advanced material stewardship in the real world.